Okay, hello again, everyone. Let's talk about the Halliday and Resnick book, once again, 10th edition. This time, let's go to chapter 25 on capacitance, and I will try to talk about problems 53 and 66. For 53, I will do something I'm going to follow my notes I generally try to follow my notes very closely. Sometimes I end up questioning, what's the best way to do something, right? And we have to kind of make some adjustments sometimes. But I sort of noticed something that I think would be kind of worthwhile to look at. It's not necessarily in the notes, but I will talk about it nevertheless. Let's talk about number 53, chapter 25 on capacitance in the Halliday and Resnick book, 10th edition. Problem number 53, a parallel plate capacitor has plates of area 0.12 meters squared and a separation of 1.2 centimeters. A battery charges the plates to a potential difference of 120 volts and is then disconnected. A dielectric slab of thickness 4.0 millimeters and dielectric constant 4.8 is then placed symmetrically between the plates. In other words, this symmetrically is perhaps somewhat ambiguous, or maybe not. Maybe that's just me having some issue with it. But symmetrically, it is exactly the same dimensions in terms of area as each plate of the parallel plate capacitor is. That's the way I take it. Where that dielectric is actually put between those plates, symmetrically now, so it covers all the area of the dielectric and all the surface area of the dielectric that's parallel to the surface area of the capacitor. They are fully in line with each other. They're exactly the same area and exactly the same shape. That's the way I take symmetrically. The thickness of the plates, the thickness of the dielectric is 4 millimeters. The separation of the plates of the parallel plate capacitor is 1.2 centimeters. 1.2 centimeters is 12 millimeters. How does 12 millimeters compare to the 4 millimeter thickness of the dielectric? 12 divided by 4, it's 3 times, the separation of the plates is 3 times the length the separation of the plates is 3 times the magnitude of what the thickness of the dielectric is. Where exactly was that dielectric put? It's not really going to matter. I'm going to say a couple things here, guys, and like I said, they're asking some questions about this. A, what is the capacitance before the slab is inserted? B, that was A. A, what is the capacitance before the slab is inserted? B, what is the capacitance with the slab in place? What is the free charge, Q, associated with problem B? C, before, and D, after the slab is inserted. So what is the free charge? So for B, what is the capacitance with the slab in place, guys? I'm sorry, forgive me. This problem, every time I look at it, I never read it right. But basically, everything that we just said, for A, what is the capacitance before the slab is inserted? B, what is the capacitance with the slab in place? Then for C and D, what is the free charge Q, C, before, and D, after the slab is inserted? What is the magnitude of the electric field? And that's part E and F now. What is the magnitude of the electric field? E, in the space between the plates and the dielectric, and F, in the dielectric itself. G, with the slab in place, what is the potential difference across the plates? H, how much external work is involved in inserting the slab? There's a lot there, guys. So let's take the look here and see what we can do. We know some things already, and we're going to utilize that. For A, we know C is epsilon naught And we'll call it CO because there's no dielectric in there. So they call it CO, but it could just easily be C. But when there's no dielectric present, C sub O is epsilon naught over D. You plug in the appropriate numbers for that, and you get that for an answer. So, let me see here, guys, forgive me. Yeah, absolutely, guys. We've been there. We're going to utilize this. We're going to utilize that quite a bit. And again, here's the answer that we got for A. Before the dielectric is inserted, what is the capacitance about which we're speaking? So, let's see here. Let's keep talking a bit. For B. Now look, the slab is inserted between the capacitor plates. Where is it inserted between the capacitor plates? They didn't really tell us. And in the end, we're really not going to worry about it. If it was put in such a manner, we'd be talking about the fact that there's a dielectric inserted between the plates means that we can treat this as capacitors in series, and look at the mathematics involved with that. It was put right on top of one plate, or right on top of the other plate, let's say. That's a pretty easy way to look at it. I think in the answer key when they were answering this, I think they made that assumption. But if we look at this in the mathematics, we don't have to make that assumption. It could be anywhere between there as long as there's symmetry. As long as the symmetry that they've discussed is in play, we're fine. What do we mean on that? Now here's where I'm going a little bit off away from my notes. Well, let me not go away from my notes just yet. I'm going to say, let's say they put the plate, they put the dielectric right on top of one plate or right on top of the other plate, and how does that all play out? Well, if you basically got a situation then when one's on top of, you got a capacitor here, the parallel plate capacitor, and then you ended up putting the dielectric right here. True. What if something else had happened? What if it was put like this? Well, it'd be a little more challenging, but we're going to get the same answer if we look at the mathematics. Let's look at this situation, and then let's look at another situation. So essentially what they're trying to say here, and again, this is not the way they're kind of doing this. We're going to say this distance, and this is not really drawn, it's not drawn to scale. Maybe I should draw it to scale. See, it's you can argue either way on that one, guys. But let's kind of just watch out a little bit. Draw it to some kind of scale here. We got this, and this is a cross-sectional view of it, and this is the 1.2 centimeter separation. Fits on top of one or another, and this is 1.2 centimeters. The distance here is 1.2 centimeters. So we got the answer to that one. Let me just get that out of here. This is D, and D is 1.2 centimeters. And the other one, okay, again, it's not, none of this is going to be a work of art, but wherever you're going to have it, let's say this is 1/3 that. This is 1/3 of D. We'll call this B. And this is 4 millimeters. 1.2 centimeters. This is 4 millimeters, which is 0.4 centimeters. 0.4 centimeters is 4 millimeters. 0.4 centimeters is 4 millimeters. 1.2 centimeters is, 12 millimeters. So 4 millimeters, 12 millimeters. Well, 12 millimeters is 1.2 centimeters, and 4 millimeters is 0.4 centimeters. So 0.4 centimeters, 1.2 centimeters. This is the way they were like arguing it. But you could just as easily argue that's the exact same dielectric, guys. All right, let me just, don't want to write over all this stuff, guys, but let me do just, go somewhere else, actually. And let's say it was right here for the other one. It's not drawn to the best scale, you guys. Again, let's get this straight. This right here is 1.2 centimeters, the whole thing. And this right here is B. Just like right here, it was 0.4 centimeters. This is 0.4. That's 0.4 centimeters. What does that mean? Well, that means that this distance right here is X. And this distance right here is Y. What's going on here? Well, look, right here, if this is B, this right here is D minus B. If this right here is B, if this right here is B, and the whole thing is D, this is D minus B. This, from here to here is D minus B, and that's B. Okay, so D minus B plus B is D, and that's this thing. The whole thing right here. Yeah. One's D minus B, and the other one's B. Well, here, kind of a different, it's a fascinating scenario in its own right. We'll call this guy, once again, B. Same thing it was over here, just a different location. And, we can argue a whole bunch of stuff here, guys. I'm not thrilled how I wrote this stuff, but perhaps there's no better way to write it, to be honest with you, maybe, given my lack of any kind of great artistic ability or anything, right? This distance is X, this distance is Y, maybe like this, maybe separate it like that. Yeah, I'll let you in on something. X plus Y is going to be, and we said this was D, and this was B. Well, if all this is B, if this right here is B, the x and the y, x plus b plus y, the whole thing's got to be d. The slab plus the space x plus the space y has got to be d. I agree. X plus y in total is d minus b. That looks a lot like this d minus b right here, which is more compactly oriented for any lack of a better statement there. So d minus b, the difference between d and b will give you the sum of x and y. Sure. Well, there's a reason I'm doing that. They didn't really get into that in the answer key. I mean, they've got more than enough to do. It's a brilliant answer key written for a brilliant book. So it's great. But let's kind of keep this in the back of our mind when we're doing some of this stuff and do the situation. We'll call this thing, I guess we call this scenario 2, the most general scenario, I guess, that you could get. Call that scenario 2, call that scenario 1, and I'm going to tell you it's not going to matter what scenario you're talking about. You're going to get the same answer regardless. So this pertains to scenario 2, and you remember how that stuff plays out. Okay. Let's talk about scenario 1 and see what they said, and then kind of tinker with it a little bit and see if we can make an argument here. Well, right here, I guess we can talk about where, regardless of where the location is on this, and it's, again, the orientation of this and everything. Call this, make this pertain, this guy here, make it pertain to capacitor 2. Make this guy right here pertain to capacitor 1. I mean, usually I like to take 1 on the top, 2 on the bottom here, but whatever. It doesn't really matter. Let's just know what we're doing. So we've got this situation for C1, this one for C2. Let's use the mathematics that's generally associated with this for finding the capacitor to kind of get us to where we want to go. Well, here there's only two capacitors, one associated with free space and one associated with the dielectric, and they're in series with one another. If they're in series with one another, when capacitors are in series, this particular rule holds. That rule definitely holds, and that's what we're going to be using. Well, you guys have the feature of what works with the film. You can go forward, you can go backward, you can speed it up and see what's going on here. So we're going to work with this scenario, and then we're going to work with scenario 2 later. I'm going to tell you it's not going to matter. But here there's a difference, guys. It's as though in this scenario, there's the way you want to look at it, let me kind of stay somewhat consistent with it. There is scenario, let's call this, it's hard to know how you want to call it here, guys, but let's call this capacitor 1, let's call this capacitor 3, and let's call this guy capacitor 2. Does it really matter what subscripts you're putting on there? No. But here there's 3 capacitors in series. Is it going to change the capacitance of the system? Is where you have the slab, which is identical area, the identical area, the identical facial area of the dielectric. The dielectric's facial area is identical to the facial area of the capacitor plate, either capacitor plate. So the dielectric is completely symmetric in terms of the surface area that is parallel to the surface area of either plate of the capacitor. Those surface areas of dielectric and either capacitor plate are equal. Those areas are equal. It is symmetrically inserted, but if it's here, touching here, or touching down there, we're going to get the same answer. In fact, we're going to get the same answer if you put it between the two. You got to pretend there's 3 capacitors here, and then when you see what happens, it's rather interesting. Okay, so we've got this situation. For that right there, so let me, you don't want to erase any of it, guys, but I got to write something. So you remember where everything is, and we're going to remember what it said right here and everything else. C3 on this one is going to be of thickness B, and this one's going to be of thickness Y, and this one's going to be of thickness X. Okay. If anything, I should remember that. I don't have it in the notes, guys. I'm just right now on the fly trying to talk about this, and I think the mathematics is rather interesting when it takes place in this manner. When we look at it, apply the mathematics that we know and the definitions that we know, the conclusions are pretty fascinating, I think. So you're looking at it, and okay, we said that they're going to be in series. This scenario 1, there's 2 capacitors in series, and scenario 1, there's 2 capacitors in series. Scenario 2, there are 3 capacitors in series. Okay. 1 over C equals 1 over C1 plus 1 over C2. And this is, okay, but does it work always? I mean, what if you move this thing around? Like I said, you could move it around. Are you going to get the exact same answer that we're about to get? And the answer to that is yes, you will. Watch. We've got 1 over C equals 1 over C1, which is, so 1 over, let's use this formula, and if the epsilon's a little different, you can just say that C equals kappa epsilon naught, kappa epsilon naught A over D, and that's for some C there, okay? So I tell you what, this is the basic structure of the mathematics based on the book and things that we've talked about. So it's the basic structure of the mathematics that's going to be applied, and the reasoning process. Area on top, separation on the bottom, there's a constant right here, and it depends what constant we're talking about. Okay, in this scenario, you're going to go 1 over, and what do we got? We got epsilon naught A over, the separation here is D minus B. Okay. The second scenario is 1 over kappa epsilon naught A, kappa epsilon naught A over the thickness of the slab, which is B. That's it. This is the mathematics. Now we have to solve it, but this is the mathematics that will solve this scenario. It'll also solve this, when it's glued right on top here, when it's placed right on top here, or when it's placed right on the bottom here. Either scenario, it'll solve it. And I'm telling you, it's going to solve it for any scenario, scenario 2 even. Let's talk about it. We'll get to that. Well, let's do the mathematics, you guys. We got 1 over C. Leave that alone. We're not doing anything with 1 over C yet until we figure out what's going on here. We've got D minus B got that. You got B over kappa epsilon naught A Okay. True. I got to have a common denominator. I don't have one. I almost do. Sort of, right? There's close to a common denominator. I need a kappa right here. Put a kappa here and put a kappa up there and you should be okay. So you got 1 over C equals kappa D minus B plus B over kappa epsilon naught A. Yeah, that's true. What does that mean? Well, okay. We got all these guys. You guys got the feature. You can always go back. So I'm pretty comfortable with what I wrote. Let me just erase some and leave as much as I can up there. Something's got to give, though. I got to, I can't keep all of this up here. I wish I could. So we got this. What's going on here, guys? Well, this right here, if you get the reciprocal of both sides, you're there. That's it. Yeah, that'll work. That's the right answer. If you plug in all the appropriate data, to at least, I think as I said, I think Halliday and Resnick answer key looks at the significant figures more than I normally do, but the bottom line is you should be getting the ballpark of here. This is right here, I don't say more important, but maybe it is. I mean, the generality here that we reach is quite important. It's quite important. Hope I can see it again. Hope I can get to it again. Well, there it is, and see if it's going to give you that kind of an answer. It worked here. It was I just extra look at it. They didn't. This is it. We're going to go with it. I am right now. I'm right now looking at it, and I'm thinking, okay, yeah, so what? Can we go further? Well, yeah, if you got 3 capacitors present, now I did something like this before, guys. I wish I could be looking at the film live here. What I had said last time. I'm doing so much of this on the fly. It's hard to remember some of the stuff here. But I think let's see if we can remember. Yeah, there was a Y on the bottom, a 2, yeah, something like that. Let me think here. This should be very much in the ball. If there's a little bit of discrepancy with the notation, it shouldn't be too much, guys. We should still be getting the right answer on that. Let's leave a whole bunch of stuff up here, and let's take a whole bunch of stuff off of here, and just kind of see if I'm getting the same answer. Well, let's see. What's up here, guys? I tell you what. If that slab is between the 2 plates, but it ain't easy to look at, it's not glued on top of the upper plate, or it's not glued on top of the bottom plate. It is somewhere between the 2 plates. Is this playing out? Is this going to work? Well, if that's the case, you got a situation of not 2 capacitors. in series, but 3 capacitors in series. I'm trying to remember how I wrote what was what, right? 3, I think, was the one that wasn't, the one that didn't, that had the slab, right? 1 over C1. C1 was, and this is the one that's got the dielectric, and the other ones don't. So it's epsilon naught A for C1, and it's a separation of Y between them. Remember, we concluded at least this much, that X plus Y was D minus B. We'll start crossing plates, we'll start crossing bridges as we need to. So there was that Y separation for that one I wrote earlier. Whether it was C1 or C2, I think it was C1. I think it was C1 on the bottom there. And then C2, doesn't really matter though. The specifics on that don't matter greatly. Just hope this works out. Again, I'm doing this on the fly, guys. I may have, when I looked at it really quickly, I thought there was something of significance there to be said. I don't think it's going to be an issue. I think it's going to work out, but let's find out. We're doing this right now. 1, 2, that's X. Remember, one was in free space, separation from the dielectric, surface to surface, separation was Y, and the other one in free space was separation from the dielectric to the, so capacitor plate to the dielectric, separation Y, and capacitor plate to the dielectric, capacitor plate, distance X. So in the middle, somewhere in the middle of the 2 capacitor plates, there's a distance Y for the one capacitor separating plate from dielectric surface. That's a distance Y, and a distance X separating the plate, the other plate, from the other surface of the dielectric. There's X that is there for the separation to take place. So the separation X, separation Y, free space to the dielectric, and then the dielectric itself is kappa epsilon naught A over B. Okay. Here we go. It's not too bad. It works out pretty nicely, guys, from what I'm seeing. Now, I don't need to speak too quickly. Sometimes I do that. I speak quickly, and I'm having to backtrack quite a bit. Hopefully this works out okay. So you look at something like this. Don't do anything with the 1 over C. We're hoping the 1 over C, the reciprocal of 1 over C is going to be this. Well, okay, don't touch the 1 over C yet. At the end, we will get the reciprocal of 1 over C and hopefully get that. 1 over all this is just the reciprocal of all this. 1 over all that and this right here yeah, pretty important. Absolutely. Let's get a common denominator, guys. Pretty close to it already, isn't it? Like we said in the past. Why don't you go kappa right here, kappa right there. Why don't you go kappa right here, kappa right there. Okay. Go 1 over C is equal to all these, we got this. Yeah, true. Kappa kappa y plus kappa x is kappa y plus x, or x plus y. We'll cross that bridge real soon. And this is B. Wait a minute. Wait a minute. You see what I see. X plus y is the same as d minus b. X plus y is the same as d minus b. 1 over c is kappa d minus b plus b. Ladies and gentlemen, I'm not going to say that it's the most profound thing in the world, because it's not, but it is pretty fascinating stuff. With the three capacitor scenario, with the more general consideration of this dielectric, the general consideration of where the dielectric is inserted between the two plates, wherever it may be, we're coming down to here. We're coming down to here. Well, hold on. Problem solved is what we have. If 1 over c is equal to kappa times the quantity d minus b plus b, that entire sum over kappa epsilon naught a, if 1 over c is equal to that, if these two things are equal, their reciprocals are equal, flip both of them upside down. Take those two, flip both of them upside down, and it's still an equation. Yeah, it's still an equation, and there's your answer. It's the exact same answer. It was important to kind of look at that. I think it's worthwhile to kind of look at that. I hadn't gone into that, like I said, in the notes. I kind of just, I did not go, I mean, they never, the Halliday and Resnick answer key, which is outstanding, and has helped me tremendously, didn't really go there. But I thought it was a good thing to maybe be a little more explicit about. Talk about it in a little more explicit, kind of talk about it explicitly, and kind of see that in the end it's the same answer. You're looking at it. Whether you got three capacitors, whether you're going to build it pretending there are three capacitors in series, and we just got the answer. It's the same as that, or whether you have just two capacitors in series in like special case scenarios. Whether it's two capacitors or three capacitors in your configuration here, you're getting the exact same answer, and you just saw it. Okay. They're asking for the amount of charge that was present before and after. So, see what we can say here. But while we're just saying this, I mean, there's a lot that has been said, and let's keep going. Let me... Yeah, I mean, we're going with that, and we see what the capacitance was. So, B, you know, plug in all the appropriate values here, and you get the capacitance is 1.2 times 10 to the 2, 1.2 times 10 to the 2 picofarad. And that's in the notes, guys. The other one is 89 picofarads before you put the dielectric in there. You put the dielectric in there, there's more capacitance. For a given potential difference, that they have talked about when you're inserting the slab, the slab in this case, given the discussion that we have given, this is 120 picofarads, and before you inserted the slab, it was 89 picofarads, so it increased. Now they're saying here, what is, you know, for C and D here? Let me erase just a couple things here, guys, so we kind of look at it fresh, I mean, while we're doing this. Okay, so far so good, guys. It looks okay. So more capacitance. 120 picofarads when the dielectric is present, 120 picofarads when the dielectric is present, and 89 picofarads before the dielectric is present. Now they're saying here, what is the free charge Q, C before and D after the slab is inserted? Then they go on. Okay, so we're basically saying before, what was the free charge on the plates? Before yeah, I mean that was the before scenario. Pico is 1,000 times let's actually have a look here. Right. Pico is 1,000 times smaller than nano, so it's kind of going to sort of explain what's going on at this point. You got Q here, and again, the idea is within the round-offs that they do when they're doing a lot of this stuff, we've got this. Let me get more chalk, guys. For some reason, I'm kind of... So we got this. That is the before. Remember, the battery did the charging, then it was disconnected. There was really nowhere, where else would this, what was going to happen? I mean, there's not going to be a flow of charge at that point, at least from the plates themselves. What is the free charge Q before, what is the free charge Q, C before, that's what we just did, and D after the slab is inserted? The same. There's not going to be a flow of charge away from there, guys. They're there. There's less potential difference between the plates as was present before, which would account for the higher capacitance. There's mathematics we could play right there. But, yeah, no surprise here. It's going to be this. Going to be this. That's D. And then they're saying for here, they're going to go E and F. E and F, what is the magnitude of the electric field, E, in the space between the plates and dielectric, and in the dielectric itself? So, okay, let's see what they're trying to say here. Let's ask that question again. It's pretty important. What is the magnitude of the electric field E, part E? In other words, the electric field gets called E, but this is part E they're talking about. What is the magnitude of the electric field, part E, in the space between the plates and dielectric? Plates and dielectric, and F in the dielectric itself. So let's see what they're talking about there before we proceed much further with this. See what we can say. I'm going to need more chalk. Okay. Between the plates and the so how they even say it here, the space between the plates and dielectric, and in the dielectric itself. So E and F on that one. E. See exactly how you want to say this. I used an X here, but I think the X is a little bit of a different. Let's see exactly. I want to be able to. So we're saying that C is Q over delta V or Q over V. We know that much. Trying to actually see exactly what I want to say here on this one. The distance that's between them. Now I used in my notes. So I got to explain why I used what I used in my notes. The X that I'm about to use here is not really the same as the X between. So let me just kind of see. It's the distance between the places under consideration. Now, it does work out the same. Let's see exactly, because voltages add up. When things are in series, voltages add up. The Q is the same. So either in scenario 1 or scenario 2, it's not going to be an issue here. The X I'm using here is not the same as the X from the X plus Y scenario that I said earlier. It's just the distance, total distance regarding the two of them, one away from the other, of the dielectric surface to the plate surface. And you can use maybe scenario 1 is a little easier scenario. Otherwise, it would be D minus B in all circumstances on this. So let's see exactly how we're going to do this. And this would not be an issue in terms of how this plays out, because you'd be looking at a scenario of something like this. Now, I think they stayed with Q1 scenario. Let's us stay there as well. The capacitance is this. V is the same as E field times the distance. We'll say the distance is X, but it's not the X I was using earlier, at least not in this situation. Not in this situation. And that equals see exactly how we want to do this, guys. I want to see what I had said before on this. There's the trick here. Let me just get rid of some of this stuff. Might be easier to look at. You can kind of say, you guys remember that we talked about, you're looking at a situation. Let me kind of just backtrack a little bit, guys, kind of how you want to talk about this. Well, if there's a lot of symmetry here, guys, that's the E times L, E times the distance D, but it's not really D. It's the D minus B that we're talking about, right? So you could, a whole bunch of ways you could play this whole thing, but we'll say it's some distance x. Actually, no, please. We do not want to say that just yet. You could say this right here is E times A, Q over epsilon naught. E equals I mean, there's a lot to be said here, right? E equals Q over A epsilon naught. I could write Q is equal to EA epsilon naught, et cetera, et cetera. You know, how much of the game do you want to play on this, guys? This is kind of where it's coming from. If you're allowing certain things to be going on, that you know, voltage pertains to something like this in terms of magnitude. The magnitude of the voltage is going to pertain to something like this. And in the right circumstances, you got E times some L, or E times some D, or E times some X. I use some X right there, what it's going to be. So don't, you know, watch out. I mean, the big thing, there's a difference there's, you know, the distance over which something's going to take place. Oftentimes you can do this. It's not guaranteed for scenario. If the E field is constant, you can pull the E field out of there. And indeed, you know, you got the E here, and you're just integrating this, and indeed you got the EL. Okay, in some of these scenarios, there's scenarios where that can actually take place, and that's where it's coming from. Okay. Again, on the notes on that, I should have elaborated on that a little bit more. I hadn't, so I'm kind of trying to work backwards for you guys a little bit. Hopefully this helps a little bit. Yeah, I mean, you're looking at this. E is Q over A epsilon naught. Yeah, that's consistent with stuff we've said in the past. Certainly that's consistent with stuff in the past, guys. When there was the generic D that we were talking about, X becomes that generic D, and you got epsilon naught A. Well, yeah, certainly that's consistent with this, you know, so for whatever that's worth, right? This is, you know, where we played the game here. We said E was going to be a constant, so if E was constant, you know, same scenario here. You can pull the E out of there, integrate the dA, and make it Q over epsilon naught. You know, if E, we're assuming between the plates that E is a constant, or in some place under our consideration, E is a constant. If E is a constant, of course, certainly. Well, that's just the A. That's kind of how the whole thing played out when you got this right here, and that's where we got how they're asking us where we're getting this stuff. Epsilon naught A or A epsilon naught. So use that one. I mean, use that and then see what we can say here, guys. Plug in all the appropriate values for the E scenario. Plug in all the appropriate scenarios and you end up getting 10 kilovolts per meter. Didn't we say that the E field times distance would give you voltage? Yeah, well, here's your E field. You plug in all the appropriate values under consideration here, and you're okay here. Given we're assuming that it's constant, notice the distance between of separation didn't really come into play here. That's E. You're going to play the exact same argument, and the E field, that's between, in the space between the plates and dielectric, and in the dielectric itself. In the dielectric itself, there's an E field, but it's not going to be as much. If we look at all the numbers. Okay, same exact argument that took place for part E is going to take place for part F, with the exception that we're dealing with the dielectric, so you have to deal with the dielectric constant to kind of play its role. The setup here, guys. So we have this. So for F, it's a different E, so I called it E prime, just to say it's a different E. And it's the same kind of argument that's taking place. It's Q over K. And again, this is consistent with the discussion that they gave us in our textbook and in the textbook associated with where these problems are coming from. And from, you know, what's said in the Halliday and Resnick book and what's said in the Katz book regarding these matters is obviously the same thing. Perhaps different approach to it, but they're going to conclude with the same thing. Well, the kappa, you already know what that is. They told you what it was. I think it was 4.8. Just make sure. Right, dielectric constant 4.8. So it's going to decrease the E field that's associated with that. So what do you got? You got 2.1. Okay, based on some of the stuff that we have said, guys. I mean, we're gonna, you know, there's more subtlety to the conversation than some brief talk on that. But basically, what we had said, looking at Gauss's law, we were able to make some conclusions. Okay, which were pretty interesting. All right, that was F. That was F. So what's going on here, guys? With the slab in place, what is the potential difference across the plates? That's G. G, with the slab in place, what is the potential difference across the plates? H, how much external work is involved in inserting the slab? Okay. So this is of interest. Way you want to look at this, voltages under consideration and everything else. So I'm trying to kind of look a little bit at this. I'm tempted, again, I'm trying to do a number of things sort of on the fly, guys, a little different from what I've been doing. We're looking at something like this, and the potential difference. So, I mean, you can kind of say, give me 1 second, guy. I'm tempted to try to look at this a different way. I mean, I'm going to do something and then maybe hook around, guys, and kind of confirm it in maybe a different manner. I know we said a number of things, and again, forgive me, guys, I'm sort of going away from the notes. When I say off the notes, I'm saying I'm not using the notes in some of these because I just think there's other things that can be said that might be of use. So let's see. I think we can reach the same conclusions as we've done earlier regarding these matters. What is the equivalent capacitance between the two places, and what could we say? So, let's talk. They're basically saying you're summing it's in series, so the voltages. Because the voltages are in series, you're going to sum the voltages. Here is E D minus B, which is outside of the dielectric. Well, yeah, I mean, there's a lot of ways to be outside of the dielectric. At the beginning of this discussion, we talked about it doesn't matter. I can make it the sum. I can make this the consideration. I can make this a problem of finding the equivalent capacitance between two capacitors that are in series. Or I could make this finding the equivalent capacitance of three capacitors that are in series, and I'm getting the exact same answer for the scenario that was originally presented to us, depending where the slab is located between the two plates. I can make it a problem of two capacitors in series, or I could make it a problem of three capacitors in series, and I got the same answer. You saw that early on. Well, here, this is the E field associated with free space, and this is the E field associated with what's going on with the capacitor. And you plug in the appropriate answers that they had given to us earlier that we had written, and they're coming out with 88 volts or thereabouts. I mean, like I said, there's the way some books emphasize things. I'm not greatly, unless circumstances really warrant it. The significant figures is not the big consideration that I'm trying to look at. It's like, do we have the right procedure to solve these problems? And we can take care of significant figures afterwards if we want. Oftentimes, that's my approach, at least from the practical standpoint, I think. So you got this right here. That's it. That's the end of the story. That's G. I just think there's something that, one of those things that it's pretty interesting to kind of, to sort of look at when you're doing something like this. Didn't we say, and that's it, I mean, we gave the answer. You know, just once again, I mean, it's 88 volts, that's the answer, you're done. All right. Now, let's stay in the non-numeric symbolism. Let's use non-numeric symbols which have tremendous power because you can put any numbers you want in there. The sum of the individual voltages, because these are in series. When things are in series, voltages add up. The Q under consideration, you know, for our purposes, so let's see what we got here, guys. So we added the voltages. The voltages will add up for us. And we had said earlier, didn't we, that, you know, we said a lot of things. I mean, we said that, you know, C was epsilon naught or kappa epsilon naught A over D, and how that actually gets proven, you know, that whole thing. We said that the EA, in at least our circumstances, we said it was this. E was, right? So E was Q over A epsilon naught. E was equal to Q over A epsilon naught. The E prime was going to be equal to Q over A kappa epsilon naught. So, again, there's so many ways that this gets written, guys. A kappa epsilon naught, and that's this guy. All right, based on previous discussions. Well, is that true? I mean, does this all work out? You got Q over the E guy is that's okay. Q over A epsilon naught. The other one is Q over A kappa epsilon naught. Again, the order of the letters, some are more advantageous than others, times B right here. Yeah, okay, that'll work. What's going on here? Tell you what, I got to get how about I get a common denominator? A epsilon naught, here's your epsilon naught, put a kappa right here and put a kappa right there. Okay. So what? Well, okay, well, not exactly so what, because it seems like we're going to... Let me think. What's going on here? Well, add them up, rearrange, and see what happens here. That right there is, let's see what we can say it is. At the end of the day on this whole thing here, guys, there's a kappa here. The well, the easiest thing I can say is this. I mean, that should be pretty obvious. A kappa epsilon naught. This is the Q. Okay, let's see what you want to say on this one. It's KQD. So I'll tell you what, the Q is throughout on this whole thing. So you can argue it a whole bunch of ways. Q's coming out of here for both of these. Then you got kappa D minus kappa B plus B. Kappa D minus kappa D minus kappa B. I got some feeling here that I might not even need to go there. Let me temporarily stop. There's more we can do here, guys, and we will do it if we need to do it. But let's stay with what we got here. A kappa epsilon naught, or kappa A kappa epsilon naught A. Not sure that's the best way to do it either, but okay, let's do it. Let's go Q. Pull the Q out of there. And why don't you just leave it like this? Because this is pretty, the D minus B was the X plus Y we were talking about. That was the way early X plus Y. Remember? The X, separation to dielectric, the other separation to the same dielectric but on the other side, because we don't know where they've inserted the slab, guys. Generally speaking, there's a separation of X from one plate to the dielectric, and from the other plate to the dielectric, to the surface closest to it, to the surface closest to the plate, on one of the plates, on one of the plate surfaces, the surface of the dielectric closest to that plate is a distance x away. On the other plate, regarding the other plate, the distance to the other dielectric, so the separation between the dielectric and one of the plates is x when you're going from plate to the dielectric surface closest to that particular plate. And the separation of the other plate from the dielectric is y if you're going from the other plate a perpendicular distance to the surface of the dielectric closest to that plate. Try saying that 3 times, I guess. I don't know. So you got this. Okay, we know that. We know that. That's a different X than what we did earlier. But you got this. You got kappa times the quantity D minus B, and then you just got a B right here. And both of these entities are being multiplied with Q. Hold on. There's an equivalent capacitance. There's an equivalent capacitance C, and let's talk. Before we really talk, let's talk some more. We already said the equivalent capacitance under consideration, regardless of the scenario, and that was important. That was important to say that. All right, guys, you're already seeing. look, this is already familiar. This looks like, I mean, somewhat. This guy, all this, and all that multiplied with the Q should be telling you something. We drew this conclusion. Yeah, we drew that conclusion. Tell you what I'm going to do. Is C, remember the Q under consideration, there's one Q under consideration for this master capacitance. It's what is the charge associated. It pertains to voltage and it pertains to charge. It pertains to voltage and it pertains to charge as to what's associated here. Let me just put it in plain English. C is Q over V. Which means if you multiply by V on each side, which means period, you got this. If you multiply by V, you've got this. If you multiply by V on each side and divide by C, you got this. Really? Yeah, I think you know where I'm going. You probably knew where I was going quite a while ago, but let's all see where I'm going right now. This is the answer, and we're going to confirm it's the answer. Based on this, they're in series. Voltages add up when things are in series. Charges add up when things are in parallel. When items are in parallel, the charges add up, but the voltage is equal. Charges add up, and things are in parallel, charges add up, but voltages are equal. When things are in series, voltages add up, but charges are equal. So charges are equal when we do this in the capacitors. Yeah, because it's going all the way across. Charges are equal, but voltages are different. When they're in series, charges are equal, but voltages are different, but you add all the voltages together. If it's in series, the voltages all add up. When it's in parallel, the charges all add up. Voltage constant, for parallel, voltage constant, charges add up. Charges are different. In series, charge is the same, but voltages add up. And we did that. We did the add up game and we got to this. Well, we got to this earlier. They derive from the same reality that I've just been repeating. What happens in series when we're talking about electricity, what happens in series and what happens in parallel? Well, I just said that a bunch of times. And that's why this stuff works out. And that's why capacitance is defined as it is. And we say, oh, wait a minute. We have to say that when things are in series, when capacitors are in series, 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3, ... to get an answer. Why is that the case? Because voltages add up. When capacitors are in parallel, when capacitors are in series, it's 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3. Why is that? Because the charges are equal, but the voltages add up. And that's because of that reality, that's why we have that mathematics. For things that are in parallel, we have the mathematics of C equals C1 for capacitors. C equals C1 plus C2 plus C3. Now, why is that? Well, here, the voltages are the same, but the charges add up, and that's why that mathematics works. And that's constantly exploited to be able to get answers like this, and in the end, come to something like this. Now, the only question is, well, that's the way we did it. That's the way we did it to get the answers that we got. Absolutely, that's the way we did it. And it started here. You're adding voltages. Again, when things are in series, when capacitors are in series, when electricity is in series, and there's something happening, there's voltages that are being encountered, you're adding voltages to find out totally what's going on. You're adding voltages when things are in series. When things are in parallel, you're adding charges. So voltages are different in series, but charges are the same. And for parallel, voltages are the same, but charges are different. So it's a different scenario. Well, here we go. It's this right here. If V equals Q over C, I think you know exactly, without further ado, where this is going. Yeah, V equals if C equals Q over V, if C equals Q over V, V is going to equal Q over C. What does that mean? Well, it means exactly what you're looking at. We got the Q, and the Q is the same. Q doesn't change, divided by the equivalent capacitance. C equals kappa epsilon naught A over kappa D minus B plus B. Yeah, true. Okay, great. You know what's about to happen. Q divided by this fraction is the reciprocal of this fraction multiplied with Q. That's obviously the same thing. That's obviously the same thing. We did not get in trouble with Q because Q was going to be the same. Q was going to be the same amount of charge on each capacitor because they're in series. Pretty important stuff. Or at least equivalent to it. In other words, it's as though at the end of the scenario here, this is what it's going to be, because we work under the assumption with capacitors that when they're in series, it's the same amount of Q, the same magnitude of Q on all plates under consideration that are in series. Better way to put it, on all capacitors that are in series, on each of the capacitors that are in series, each capacitor has the same amount of charge as any other capacitor that is in series with it. Okay. So we looked at it, we got that. It's a little different. I went a little on the fly on that, guys, just to kind of look at it. So, I mean, how much external work was done, and so let me kind of see here, guys. For H, so with the slab in place, what is the potential difference across the plates? There it is. If the slab was not in place, what would it be? That's another. With the slab in place, what is the potential difference across the plates? If it weren't in place, it'd be Q over epsilon naught, Q over epsilon naught A. Kappa times smaller, yeah, not quite. How this would all play out here, guys. You're going to get a smaller answer. Yeah, there's a smaller voltage when it's there. So there's been a drop in potential. So what's going on here, guys? There's a drop in potential. I mean, it would have been a situation, how this answers, guys. Again, it's a little more depth to the problem. I mean, you don't want to sit down and philosophize about this too much in the middle of an exam or something, but it is good to know now, just away from a pressure situation, to see what's going on in this situation. Well, here it is. There's the voltage when it's present. If it were not present, what is it? You know? Well, you'd be talking about, in a situation such as that, you'd be talking about, didn't we say the CO, just by itself now, before the slab is present, it would be that. And CO would be Q over VO before that was going on. Yeah, that's essentially where we were. That's where we were, guys. And let's figure this out. Let's solve for V0. VO, this is before the slab's inserted, guys. Solve for VO, what do you say you take the reciprocal of both sides? You got VO over Q equals D over epsilon naught A, then multiply by Q. Here's VO. This is not, you know, we could talk, there's a lot to be said. Regarding these matters, I guess you could say, guys. So let's see here. Let me think. So you got this. I mean, can we do a comparison here, maybe? Put a kappa right here. Kappa epsilon naught A. Kappa epsilon naught A. Yeah, all right. Okay. Kappa epsilon naught A. Put a kappa here. Q kappa D. This is Q kappa D minus a number bigger than 1 times B plus B. What's going on? What happens there, guys, is when you add those, you get a situation. This is kappa D, and this is, like I said, you could kind of play the game here. For the heck of it, put the kappa here. Put a kappa on the bottom, but put a kappa on top too. Kappa D, huh? How do they compare? I'd like to know. I mean, this is pretty elaborate. Doesn't mean it's bigger. In fact, it's smaller. Watch. This is kappa D. This is kappa D. Kappa D minus kappa B plus 1B is it's minus kappa B plus 1B, so it's kappa D. Yeah, I got that here. Kappa and kappa cancel. I got QD. I got QD over epsilon A. QD over epsilon A. Yeah. Put the kappa in there just to see what it was. It was QD over epsilon A. Put kappa here, put kappa there. Okay, here we go. I got him. Yeah, true. Kappa times B is kappa B minus kappa B plus 1B minus kappa B plus 1B is interesting. It's really minus kappa minus 1 get it straight. Let's get it straight. Kappa is bigger than 1. Kappa is always bigger than 1 for our considerations here. If kappa is always bigger than 1, then something always bigger than 1 minus 1 is always positive. Always positive times B is always a positive answer. Subtract a positive answer from here, and you get a smaller answer than that would have been without this present. This guy right here is bigger than 1 minus just 1 is an answer that's still positive. Positive times B is a positive answer. Subtract positive, subtract a positive. Subtract the positive from this, you get a smaller answer than this. This is what it was. This was the voltage between the plates before the dielectric was inserted, and this is the voltage between the plates after the dielectric was inserted. Absolutely true. What does that mean? It's a lot of ways to go. I'll make a long story short, guys. V0 is bigger than V. Because I can write this is the same exact V, guys. I haven't changed anything. This V can be written like that. And that, because of that positive answer, and all that because of this positive answer being subtracted from this, and this right here. So in other words, the difference between the two, the initial voltage, the potential difference, let me see how they use the exact same language they're using here, guys. The potential difference initially, before slab inserted, is bigger than after. True. What does that mean? There's a potential drop. Things tend to like a potential drop. They tend to go to lower potential. They tend to want to see it like this. What does that mean? Well, that means that Q kappa D over is greater than Q kappa D over kappa epsilon A minus kappa D, right. Not as much of a minus. Minus kappa 1, kappa minus 1 rather, I'm sorry, times B. That's pretty obvious. Well, obvious. I'm not sure how obvious some things are, but guys, you know, depends how long we've looked at some of this. When we get, myself included, the more I can look at it after not, you know, if I haven't looked at something for a long time, anything, even if you know something, it's good to look at it again. Clearly, there's a difference here. Clearly, there's a difference. Where's the difference? You're looking at it right here. This is a positive number. Kappa is bigger than 1. Something bigger than 1 minus 1 is a positive number. A positive number times a positive number is a positive number. Divided by a positive number is a positive number. You're subtracting a positive number from this. The difference between the two, what's the difference between the two? Well, V0 is this much bigger than the other one. V0 minus V, V0 minus V is going to be this positive number. Absolutely true. Yeah. Well, yeah, there's a potential drop. Things tend to go to lower potential if you have the opportunity to go to do so. Things will, you know, this system will go to a lower potential if it has the opportunity to do so. It will have the opportunity to do so if you insert the slab. The slab is welcome. So that's where we can answer this question then. I mean, how much external work is involved in inserting the slab? No external work. The system will draw the slab toward it. You don't have, the slab does not have to be forced into the system. The slab does not have to be, you know, there's no external work that has to be given to it for this to take place. Once the introduction is made, the slab is accepted, and there's less, you know, the amount of energy external is basically there's a drop in potential. Okay, when this happens. So what's the external work that's done on this? So they're saying, how much external work is involved in inserting the slab? Don't want to erase any of it, guys. But, I mean, you got it, you set it up, you already have it. Now, the way I have it in the notes, I didn't go in this kind of detail. To take the slab out will require work, but not external work, positive external work. But to bring it in, it's negative external work. What's going on here? The way this plays out is work external is 1/2 Q delta V equals 1/2 Q, same Q, the system. The original system, so it's final, the final system is V. The initial is V0. There's a lot going on here. Well, yeah. Didn't we say that isn't V the same as, I mean, didn't we already say that C was equal to, in general, right? C was equal to Q over V, which implies that V equals Q over C. That's Q over C. Okay, we've been there. Yeah, we not only been there, guys, we just figured out what it was. I mean, this is the absolute value of the difference. This is a positive number. V0 is bigger than V. If you switch it around, V minus V0 is going to be the opposite of this. The opposite of a positive number is a negative answer. The opposite of a positive number is a negative number. So this is negative. I mean, wherever you want to go here, guys, we're gonna find it. I mean, the initial potential difference present before the slab is inserted is a larger number than the potential difference between the plates after the slab is inserted. The difference between the two is this positive answer. Initial minus final is a positive answer. Switch it around, final minus initial is the opposite of this positive number. It's a negative answer. This will be a negative answer. This is where it comes from. The whole thing here where you plug in all this, that's your call. Where are you going to put these? It's a little different than what I didn't go into this kind of detail in the written notes, but it's there. I mean, you got the 1 over Q. And we said V minus V0 is going to be a negative answer. It's going to be the opposite of that. It's going to be negative kappa minus 1 B over whatever. I mean, whatever the numbers that you have. The big answer here, negative 0.17 times 10 to the negative 7 joules. Yeah. It's a great question. Doesn't require, get it in the right place, it's accepted. That's the situation where there's going to be a drop in potential. How much external work is involved in inserting the slab? A negative 1.7 times 10 to the negative 7 joules. Simple as that. The situation is what is preferential to the system for something like that to happen once the slab is introduced. Okay, that's 53. 66. Should go a little bit faster. It's a little simpler type question, so let's go for it. For problem number 66, a cylindrical capacitor has radii A and B as in figure 25 25-6. Show that half the stored electric potential energy lies within a cylinder whose radius is R equals the square root of A times B. Okay, let me try to figure this one out. Let me write some of this out, guys, when we actually do this. Okay, guys, I'm just going to use all right, guys, let me try to draw a little bit of the figure here. For number 66, a cylindrical capacitor has radii A and B, as in figure 25-6. Show that half the stored electric potential energy lies within a cylinder whose radius is R equals the square root of the product AB. So if you were within the cylinder, can you actually figure out what's going on and actually make it look a little different here? In other words, get half, show that half the stored electric potential energy lies within a cylinder whose radius is R equals the square root of the product AB. So looking at this, guys, let me try to find it. For some reason I had this down here. I don't know if I had actually drawn it in the notes. I think I have not. So let's take a look. You see the figure they got, and I'll try to Okay, guys, let me just say something really quick here. They talk about a cross-section of a long cylindrical capacitor showing a cylindrical Gaussian surface of radius r that encloses the positive plate and the radial path of the integration along which equation 25-6 is to be applied. The figure also serves to illustrate a spherical capacitor in a cross-section through its center. So you can kind of play the game either way with this. So you could use it as a spherical capacitor or as a cylindrical capacitor. At least the figure itself can kind of let you get away with it. Speak of at what location, I guess you could say, is the potential energy that is present. So let's say let me actually write it down. It's the way the question is asked is. rather interesting. The book itself on page 721 of the Halliday and Resnick book, pages 721 and onward a little bit, just for another page or so, 722. So 721, 722. Let me draw that and let's talk a little bit of what's going on here. At what location can you say the amount of energy is stored from like a particular distance? At what distance within that capacitor is half of the potential energy to be found? Pretty fascinating question. So let's take a look at it. Let's take their drawing of it a little bit. I don't have the drawing of it in my notes, but I got a lot of the mathematics to it. In fact, all the mathematics pertaining to it. So let's take a look at this a little bit. Okay. They're saying essentially something like this. I don't want to, it's debatable how I want to actually say some of this. How the drawing can proceed, I guess. It's solid, but I got to make it kind of light when I do this kind of thing. And not a very good drawing, guys. It's supposed to be kind of spheres all over the place here, I guess. This radius right here is A. This radius right here is B. Tempting how you want to write this stuff, guys. That's A. That's B. As far as the radii are concerned, pretend it's a spherical drawing, or at least some semblance thereof. Look more like spokes than negative signs, guys, but these are negative signs. Total charge on the outside, total charge on the inside is positive Q. Total charge on the inside here is positive Q. Total charge on the outside is negative Q. We can figure out, and you're basically, there's a lot of ways to figure this out, but for our purposes this way, and we're going to do you're going to do integration going perpendicular to the two surfaces. Integration is going to take place going perpendicular to the two surfaces. Positive Q total charge on the inside, negative Q total charge on the outside. And what we have here okay, a cylindrical capacitor has radii A and B, as I've drawn, consistent with what's in the book. That's me saying that, consistent with what's in the book. Cylindrical capacitor has radii A and B, as in the figure that I consulted and tried to draw here at least some level. Show that half the stored electric potential energy lies within a cylinder whose radius is R equals the square root of A times B. We're thinking somewhere pretty fascinating question in its own right. We agree that B is greater. We agree that B is greater than A. So B squared, the square root of B squared is greater than the square root of A squared. Why is that true? Because the square root of A squared is A, and the square root of B squared is B. So yeah, we know that's true. Okay. True. Is it true? So if you square the two, if you square this side, you got B squared is bigger than A squared. Yeah, that's obvious. A is not that big, and B is really big. So if B is, there's a lot you can say here, I guess. I mean, if B is bigger than A, then if B is bigger than A, then B times B is bigger than B times A, and B times A is bigger than not multiplying by B, but multiplied by A. A times A is A squared. This is AB. And this is B squared. That's kind of interesting. Is that true? Yeah, of course it's true. Again, if B is bigger than A, then multiply by B over here and multiply by B over here, then BB is going to be bigger than BA because A is small compared to this B being big. And B is bigger than A, so if A and A are actually equal to each other, if you multiply this guy by B, if you multiply the A by B, which we've already done, and you multiply this guy not by B but by a smaller number than B, if you multiply the A by B and multiply this A by a smaller number, you multiply the A by B and you multiply this A by a number smaller than B, A for example, you get this. Interesting. What does that mean? Well, that leads us to the conclusion that B, look, if these are two positive numbers. If two positive numbers are like this, they're square roots. I mean, basically what we got well, these are both positive numbers. And if this is bigger than that, B is going to be bigger than this. And we said AB was greater than A squared. If you square root both sides, they're both positive numbers. If these two positive numbers, this one's bigger than that, its square root's going to be bigger than that. Well, okay, this maybe alleviates any fear, if there is any, regarding how big this guy is. The square root of the product, A times B. There is a number between A and B. This is A, and the whole thing is B, and there's a number between A and B within the cylinder that we'll call R. R equals the square root of the product, A times B. Okay. Yeah, sure. We know, based on what I just said, that R is going to be less than B but greater than A. All right, I mean, maybe that helps a little bit with what we're doing. All right, well, let's deal with it based on things that we know and that we've done. Okay. Well, a cylindrical capacitor. Now look, this is fascinating, the whole process here, guys. Show that half the stored potential energy lies within the cylinder, whose radius is this. Okay, so let's see what we can say here. We said that U, the stored energy, is 1/2 Q delta V. Equals 1/2 Q delta V, the potential difference, E times D. Which, you know, there's a lot of stuff that goes on here, guys. We could see a whole bunch of stuff here. We could say that U is 1/2 Q, delta V is Q over C. Remember, C is Q over delta V. C is Q over delta V. The Q's cancel, delta V goes on top. Sounds about right. Equals 1/2 Q squared. Man, we've been seeing this all over the place at some level, right? I mean, talking about the capacitor here. There's no dielectric present, so we're right here. There's a lot to be said here, guys, when we do some of this stuff. Let me see. We have said earlier, we want to see some of this. We've already concluded earlier and we played this game quite a bit. That easily can be concluded from EA equals Q over epsilon naught, and then do it. Absolutely. So, okay, I mean, it's what it is. Let's talk a bit. You can look at, okay, we're saying all this, so let's Again, some of this, I'm going a little bit off the script, you guys, on some of this just to make sure we're okay. Okay. Then let's see what we can say here a little bit. Just to get like some kind of gut feeling for some of the stuff that's happening here, guys. Let's find the potential energy stored per unit volume, which is going to be equal to, which is small u, which the potential energy stored per unit volume is big U. We'll call this potential energy stored per unit volume is small u, and that's equal to big U divided by the area. If you were talking about like parallel plates and stuff like that, this is some of the gut feeling for what happens here. Then I'm drawing this conclusion for something that is, you know, it's flat plates moving over a distance, moving in a direction perpendicular to the face of the area. The face of the plates move in consider a volume perpendicular to the facade of the plate, so to speak. Well, I'm going to draw a conclusion, and we could say it's true generally, is what we're about to say. U is this. When you divide by, so you got this. When you divide by AD, that's kind of what's going to happen. So let me leave this alone a little bit. AD on the bottom, huh? 1/2 Q squared. If you put an AD here and another AD here, the D's cancel and you got A squared on the bottom. So just to know that. So what do you got? Well, the D, we just said that. So it's epsilon naught, A squared, and the D canceled. What's going on here? Well, what's going on here is this. Let's match it up. Q 1/2 Q squared over epsilon naught A squared. Multiplied by epsilon naught on top, multiplied by epsilon naught down here, and epsilon naught right here. This becomes epsilon naught squared, and the epsilon naught's here. What the heck just happened here, guys? Didn't we say, by hook or crook, for a simple capacitor, not as complicated as this one, but we're told that it's all right. The conclusions generally apply. Many of the conclusions generally apply to more complicated situations. This is Q, this is epsilon naught, this is A. Q over the product, epsilon naught A, is equal to E. E equals Q over epsilon naught A. Q over epsilon naught A, wait a minute, but what if you square Q? What if you take Q over epsilon naught A and square it? Q squared, epsilon naught squared, A squared. Wait a minute, this was equal to E. E equals this. If you square E, you get Q squared over epsilon naught squared, A squared. Q squared over epsilon naught squared, A squared. That's E squared. Yeah, it's a bit of a mess, but maybe we need to talk about it. Here's a half. Here's epsilon naught. Q over epsilon naught A. Q over the product, epsilon naught A, is E. So Q squared over epsilon over the product, epsilon naught squared A squared, is E squared. Well, there's a lot of conclusions that get drawn along these lines, and they apply generally even to more complicated matters than just the parallel plate capacitor. This certainly works for the parallel plate capacitor. I made the argument vis-a-vis the parallel plate capacitor, and it works. Well, that's pretty significant. If for no other reason, I mean, this and this has pretty broad application. That's generally the case. At least if we can, you know what? I mean, certainly it's if you're not too believing of the matter, I mean, it's generally the case, certainly if we can make something approximately, or at least part of something. If we make part of something look like a parallel plate capacitor. If we're talking about infinitesimal displacements between two curved surfaces, they resemble a parallel plate capacitor, and this will hold. Well, let's see. That's about what we're going to do, but we're going to have to do it infinitely many times, so that there's an integral involved. There's an integral involved, obviously, in doing something like this. So if this is the case, okay, we said a lot of stuff, guys. And by saying those things, we drew some conclusions, at least for the simple case scenario of a parallel plate capacitor. This is very believable based on what we know about parallel plate capacitors. This is very believable. Okay, can we approximate at least something? Can we approximate at least part of something over a very small region? In any very small region, do we have, you know, is this something that works? And if we just do the right kind of integration, we should be all right. All right, there's a lot here, guys, and you know, maybe my choice of words is not the best on this, but we've got this. We believe it. Now, you know, this is a varying situation that we have here. We have a lot of stuff here. We've said things here. Let's, I think just actually doing it, I think we're in pretty good shape here, guys. I'm sorry, I'm running out of items with which to actually erase that are actually functional. I'm going to have to get a hold of some better items here the next time I do something like this. Okay. Is it true for a particular region at least, can we look at a few things? Well, we said here, be aware of that. Be aware of this. All right, so we got this. Is it true that, based on things that we've been talking about quite a bit, and I'm going to try to find, like everything that is confined here. The Q stays the same. The Q's not changing because it's positive Q is what's caught right here. And so we'll kind of take it from there. Well, yeah, for a particular, for a small enough region here, guys, let me just try to see. There's got to be, for a length L of, okay, so this is, let's talk a little bit. For a given location radially away, a distance r, some distance r between radii a, this is radius a, and this whole thing is radius b. So between radii a and radii b, there's a distance r, and it's going to vary. It can vary, and we'll say for a particular location, there is a radius r between the two, and we're going to prove this is going to have half the potential energy in its possession within this thing if you can find the radius. And we're going to say the radius is going to be the square root of the product A times B. For the radius r present somewhere, this is the radius r present. I don't know what it is, but it's radius r. If I go 2 pi r, I know the circumference of the circle, and if I multiply it by a distance, capital L, I know the surface area of the cylinder that contains that charge. I know the surface area that contains that charge. It's a very long charge. So, if that is the case, the E field is constant at that radius, at any particular radius r. It's got a particular constant value. It's got a different value depending where you are, r-wise, but 2 pi r times L. The outskirts of it here, the stuff perpendicular, to the axis, either way is not going to matter. They're going to cancel out. The E field is going to cancel out. But the E field here is going to have significance. Okay. So 2 pi RL equals Q over epsilon naught. True. If that's the case, you guys, and it is, E is going to equal see, the E fields are going to cancel on the outskirts of it. It's just the top that's going to have significance. And we're going to say that's going to be Q over 2 pi RL epsilon naught. True. Do something here then. Small u is 1/2 epsilon naught E squared. Is 1/2 epsilon naught. There's your E. Square it. for pi squared r squared L squared epsilon naught squared. The epsilon naught and the epsilon naught squared cancel, and you got this. You know, it's you know, there's a lot here. Let me think. Got the 1/2 here. You got a whole bunch going on here. All right, you got the 1/2. You got the 1/4. 1/2 times 1/4 is 1/8. The q squared stays on top. You got pi squared. You got L squared. You got epsilon naught. 1/2 times 1/4 is 1/8. That's a constant. The q squared is a constant because wherever you want it, the E field changes. The E field is constant along any particular radius, but it's a different constant if you change the radius. It'll be constant in that other radius as well, but it won't be the same number as it was earlier. For any radius, the E field is going to be constant. That's and the charge enclosed is constant. You got Q as that. So we did all that, and that's the L of this and the 2 pi r. And we didn't worry about the pi r squared on this end and the pi r squared on the other end. We didn't worry about this guy, the face of this guy over here and the face of the other guy over here. So the E fields are not going to be, there's no E field, there's no flux, there's no net flux at that point because there's other items within this. The very long, like I said, what did they say here? Well, I guess they made the assumption it's very long, so it's not something that, it's not, we're ignoring the fringing effects, and if it's a very long within that particular place, there's going to be cancellation of E field and stuff like that. So that's not going to be a case for us to worry about. The big thing here at the end of the day, guys, is can we get this thing to work? I mean, and we got, that's a small u now, right? I write everything pretty big, so I don't know what's small, what's not regarding this, but it's a small u, and we'll take it from there. So get small u, and what is that? Well, it's, you know, it's a lot. I mean, it's 1/8. We said the q squared stays strong, stays unchanged. You got an 8 here. 1/2 times 1/4. 1/2 times 1/4 is 1/8. This is pi squared, r squared, L squared. Pi squared, r squared, L squared. Pi squared, r squared, L squared, epsilon. I'm going to put the r squared right here. You notice I said r squared but didn't write it down until now. That one varies. 8 pi squared, capital L squared, epsilon naught, and q squared are all constants. Q doesn't change. You're containing positive q right here. Here's negative q out here. Yeah, that's all well and good, but you're not reaching up to negative q. You're only dealing with this. Positive q right here. So positive q, q is what you're containing every time. The 2 pi r is the circumference times the perpendicular length coming right out at you, capital L. Capital L times 2 pi r is the surface area of the cylinder, not counting the ends of the cylinder, which don't come into account, according to the assumption for this problem. Okay, so they're not coming into account. So you're just dealing with that. So you got this, that's small u. If that's the case, let's find the entire stored energy and figure out what's going on. All right, so basically, guys, this is pretty big. I mean, this is very important stuff. Once we get to here, I mean, like I said, I don't like to erase any of it. I mean, it's got pretty, at that particular place, what's the E field? How much energy is stored there? Pretty fascinating stuff. What's the amount of E field? Notice the location tells you the strength of the E field and how much potential energy is stored in the E field, or what is the potential energy per unit volume at that location. Yeah, that's just one that's just one sliver of a location, guys. There's, on the other side of this, you can build, I don't want to draw too much actually, but if you went this way and just made a cylindrical shell, within that cylindrical shell, more or less, this is an approximation of how much stored energy per unit volume you have when you're close to that radius r. If you're at another radius r, there's another, most likely, depending on the situation. In this situation, definitely. If you go somewhere to another r here, there is another potential energy per unit volume. Different answer, different amount. Different, it's the same mathematics basically, but it's a different amount of potential energy per unit volume if you go outward. If you go to this guy right here. If you go out to here and you look at the shell that's here, the amount of potential energy between the two edges, between the two shells, between the two edges of the shell. It's a shell between the inner part of the shell and the outer part of the shell. How much potential energy is stored per unit volume in that infinitesimal differential volume that is described by how much volume is there between the two shells. The potential energy per unit volume is roughly, not exactly, because the more you change R, as you change R, the small u changes. The potential energy per unit volume changes. Okay. So, but approximately the potential energy per unit volume for a shell that's very thin and the radii under consideration are close to the R under consideration here, then there is a set U roughly, which is potential energy per unit volume for that shell. As you change, as you move on, the potential energy per unit volume for another shell is different. But if you if you take the potential energy per unit volume and multiply it by the volume under consideration, infinitesimal volume under consideration, you get the potential energy there. If you do it, if you subsequently do this and add them all together, that's called integration, and that's going to give you the total potential energy that's present within that configuration. Okay. Make a long story short, let's just do that. So we have this. We talked about that. We brought this, and this is really going to get us through the whole process, you guys. So what we can say, okay, I think we're all right. I think all we got to do now is just do the integration that we need to do, and we can figure out what's happening here for the entire stored energy. The entire stored energy, U, you can call it delta U if you want. I mean, just a change in potential energy from one place to another. If you run the whole gamut, if you run from all the way to here, you're going to encompass all the potential energy that is available. Delta U or U, we'll call it delta U here. I think that's the way the key went about it. It's going to be the integral within the appropriate limits of small u delta v, differential change in volume. It's going to be the integral of, you got all this right here, this is q squared over 8 pi squared L squared epsilon naught 1 over r squared. The differential change in volume is 2 pi r L, that's area, changing over dr. Remember now, this is the differential area. It's not really the different, I take that back, it's not really a differential area, it's an area. And that area moved through a distance perpendicular to that area. This is the area, 2 pi r capital L. That's the area under consideration. We said we were ignoring a lot of stuff. We made conclusions earlier, and we ignored some things, and we said we were justified in doing so. So here we are. We have the area 2 pi r L. 2 pi r times L, wherever you want to go here. For any one of these r's, I guess. Let's go here. I mean, here's 2 pi r times L. That's the area of the cylinder, ignoring the sides, okay? Just that's the area of the cylinder. And then if you multiply by dr going perpendicular to that cylinder, you find a differential volume element. And that's what we just did. That's all that we just did, guys. So we got that. The heck is going on here? There's a lot going on here. Delta U, let's see what we can say. There's a 2, there's a pi, there's an L, there's a dr. Tell you what I'm going to do. There's a 2 that goes into the 2 and the 8 cancel and you get a 4. The pi and the pi squared cancel and you get a pi. The L and the L squared cancel and you get an L. The epsilon naught stays as is, the q squared stays as is. The r and the r squared cancel and you got a 1 over r. At the end of this dance, you guys, you've got a situation where it's, let me just hopefully make it a little easier here. Here's q squared is a constant for our purposes, for the circumstances that we're in. For the circumstances that we're in, the q squared is a constant. 2 times pi, 8 pi squared, the 2 pi and the 8 pi squared is going to be the 2 and the 8, you got a 4 on the bottom. The pi and the pi squared, you got a pi on the bottom. You got 4 pi. And the L canceled with the L squared. 4 pi L. The end of the dance there. Epsilon naught. We'll double check that, guys. I don't want to do anything careless here. The R and the R squared cancel. All right, that's pretty manageable. We're going to go from A to B. I saw other things mentioned that didn't seem to make a whole lot of sense to me. Some of the discussion, but perhaps I'm missing something. It's not uncommon. But I think this is the way to go. This is the way to approach this. Yeah, this is it. Yeah. If you do the integral and evaluate, look. The integral of 1 over r dr is ln r. Evaluate it between these two limits, you get ln b minus ln a. The difference of two logarithms is the logarithm of the ratio. to make a long story short, when you actually play that out, you got Q squared 4 pi L epsilon naught ln B over A. That's the entire stored energy. Great. I want half of it. That is the entire stored energy. If they're asking us, if they asked us, we got the answer. We just did it. That's the entire stored energy. Kept going. You know, the energy per, that made a lot of sense. I mean, how that actually plays out. If it's constant. How much, between two capacitors. And it works with the cylindrical capacitor as well. If you pretend that, if you go from area, move from the area of one part of a very, very thin cylindrical shell, move from the area of the inside portion of the very, very thin cylindrical shell and move to the outside portion of the very, very thin cylindrical shell, which isn't a whole lot difference in terms of area, and you're going perpendicular to that particular area, it's a good approximation that you're getting the area, it's a good approximation that you're actually getting the volume, and the E is constant for that particular very, for lack of a better word, very confined volume, very differential sort of volume that's very, very close to R. And you just keep doing that throughout the process for all the R's that are present from here all the way up through here. And you're just going to walk it that way. And that's what I did with the integral. And that's the thing for the whole thing. And that's the entire stored energy. You only get 1/2 of that. And that should go pretty smooth, guys. And from then on, it goes all right. And like I said, we said a lot of stuff. Right. I mean, I said a lot of stuff. The rest is pretty straightforward, guys. Let that be for the large area under consideration, and let's not get this done. I mean, let's take it. Let's find out where this thing is. We already said that. Hey, man, they are proposing to us. They're saying, prove to me, prove to me, prove to us that that's the answer. Well, first of all, we looked at it and we proved that the square root of the product, A times B, is a number indeed between length A and length B. It's somewhere located in here. There's some R located in here that's between the length of A and B. We already proved that right in the beginning. So we've got this. Can you find the half? Yeah, it's all right. We're going to prove that right there. So it is a different answer, but again, if you can get situations that resemble very simple situations, within a very complicated situation, we can find approximations. Well, let's put it this way. Within very complicated situations, as we have over there, we can find in very, very small spaces, in an infinite number of very, very small spaces, we can find approximations to the easy things that were given to us earlier. And those easy things correspond to the very small spaces. At that point, we just do an integral with each one of those things that correspond to the very small spaces. Using that logic, we do the right sort of mathematics, and we should be okay. And we are okay. We got this for an answer. So if that's the case, what do you want to say about it? Well, you got to make a long story short here, I guess. If that's the total, then 1/2 of delta U is going to equal this. These are all constants, guys. Q squared, 4 pi, L, epsilon naught. They're all constants. I went half times du. Half of this is half of du, but half of this is also half of that. So I'm going to go half of this. Look, this is what you got right here. Multiply this by 1/2, then you have to multiply this by 1/2. If these two are equal, if you multiply this by 1/2, you got half the potential energy. But you also got to multiply this by 1/2. So you put a 1/2 right here. And that's what I did right here. Okay, guys, I think I need another piece of chalk. Oh, wait a minute, this is okay. So you got to put that there. Let me just get that out of there. Yeah, if I was doing a half here, I got to put a half there. Okay, but this is the original for all of it. Okay. Half of this is half of that. Okay. True. Now here's where it gets interesting. Half of the delta U is, here's delta U, and you got all this. Half of the delta U is half of this, which means half of the delta U is half of this, which is that. Okay. True. And that's going to equal Q squared, 4 pi L. That doesn't change. Remember, that was kind of just in there. We were doing it. Times ln of integrate from A and go to some capital R. I put capital R there, meaning it could be small r. It's going to be use small r, doesn't really matter. I used capital R, so I'm going to stay consistent with that. Wait a minute. This times a half of that is the same as this times integrating to some particular place. I don't know what it is. Guys, there's a moral to the story here. This is equal to this. And that right here is equal to that right here. So that's where the whole thing has to go. Basically, you're saying these don't change. These don't change. If it's 1/2 of that, all of this and all of this cancel. Half of this is this going to something that'll give you half. What are we talking about? We're talking about ln capital R over A, because the integral, you know how the integral goes. The integral goes from A to B. Well, the integral from A to B, or the integral from A to capital R, is what? Well, the integral of 1 over R dr is ln R evaluated between A and capital R. That's ln capital R minus ln A, which is the difference of two logarithms is the logarithm of the ratio. ln of the ratio, capital R over A, equals 1/2 ln B over A. Okay. What do you say? Well, yeah, there they are. That's what it is. Is it true, you guys, if two things are equal, they remain equal if you do the same thing on each side? If these two are equal, you can exponentiate each one of them. E to the ln, the quantity capital R over A, is the quantity capital R over A. E to the 1/2 ln, the quantity B over A. Wait a minute. Isn't 1/2, I mean, we can do, let me time out here. I don't know if it's a valid time. This works fine. Inside of here, my friends, what's going on here? Is it true that we got E to the ln capital R over A? And is it true that this right here, 1/2 ln the quantity B over A, is the same as, just leave the E alone, just the E's down, the E's already down there. The 1/2 is B over A. Yeah, forgive me, guys. There's a lot of ways to go here. There's nothing wrong with what I was doing here. I don't know that there's a good conversation here to be had if I don't think it's an optimal conversation. Let me stop there for 1 second, and then let me all right, guys. Let me momentarily stop right there. Where did I get it from? I got it from this equals this. Okay, I'm momentarily stopping right there. Then I'm going to say ln capital R over A, a number times the logarithm is the same as the logarithm of the quantity exponentiated to the number that was in front. There's a better way to go. That was the way to do it. If that's true, and it is it true that if you take ln R over A and ln B over A to the 1/2, based on things we've done earlier, yeah, you saw me do that. 1/2 times ln of the quantity B over A is the same as ln of the quantity B over A taken to the 1/2. In other words, you're not exponentiating the logarithm, you're exponentiating the quantity whose logarithm you're getting. 1/2 times ln of this quantity is the same as ln of the quantity taken to the 1/2. ln of this quantity taken to the 1/2, the ln of that. That's what it means. So, just want to make that very clear, guys. You know it anyway, but let's cover ourselves. Right? This is E. This is E. All right, let's have a look here. That's this guy. Okay? What are we talking about here, guys? Didn't we say look, let's get it straight. If two quantities are equal, they remain equal if you do the same thing on each side, assuming no crazy results happen. There's certain limitations. You don't want to get some sort of forms that are very indeterminate, where limits get kind of crazy and stuff like that. When we're talking about finite numbers, if two finite numbers are equal to one another, if you do this, if two quantities, two reasonably behaved quantities, if two reasonably behaved quantities are equal to one another, then they remain equal to one another if you do the same thing on each side. Okay. These two are equal to one another. I'll do the same thing on each side. What is that? If these two are equal to one another, that means E to one of them is equal to E to the other one. If A equals B, then E to the A equals E to the B. It's reasonable. The exponentiation of a logarithm gets you back to where you started. Assuming we're talking about, corresponding bases, corresponding bases of exponentiation and corresponding bases of the logarithms, of course. This right here gives you BA to the 1/2. What does that mean? R over A equals the square root of B over A. That's the whole thing to the 1/2. Multiplied by A on each side. The square root of a ratio is the ratio of the roots multiplied by A on each side. How many times does the square root of A go into A? Square root of A times. Square root of B times square root of A is the same as the square root of A times the square root of B. Capital R is the product of two roots is the root of the product. You're done. That's capital R. I called it capital R. They called it small r. It means the same thing. For our purposes, we're just going to say small r, capital R, and there's the answer. And there was a number of things there, guys. I thought I hooked around, I hope in a decent manner for you to understand that, okay, we're just approximating. We are pretending we're dealing with a capacitor that's easy to deal with, or at least has some element of how a capacitor be. We're looking at a capacitor. Let me actually see here, guys. I think we actually, in kind of a rather clever manner, the capacitor in some sense manifested itself. Right. I mean, it was, even here it was manifested. So if it's a simple, well-behaved parallel plate capacitor with a distance d between the plates, we can find out what the E field is. Well, I'm saying we can approximate and say that, we can use much of earlier mathematics for simple situations. We can use it in a more complicated situation, such as this, which is definitely more complicated. We can use it, and for very, very small spaces, the earlier mathematics that was easy works. The problem is those very, very small spaces occur in different places, and in different places we've got different numbers, so they're not constant. So we've got to do a sum of infinitesimal quantities. It's called an integral. So the mathematics is there, it can be done, and that's basically what we're talking about. And as I said, we do come down to it. We come down to here. I called it capital R, they called it small r, it's the same thing. Okay. Thank you very much for your time, guys. We'll talk.